All right, let's jump right into this explainer. Today, we're exploring the high-octane, universally engaging world of Formula One design, and we're going to uncover a fascinating piece of tech that isn't just, shaving fractions of a second off a lap time. It's fundamentally reshaping our global economy and how we manufacture almost everything. Okay, picture this. Imagine trying to test the performance of this multi-million-dollar Formula One car. Historically, if you wanted to know if a new wing or chassis design actually worked, well, you had to physically build the thing. That meant machining parts, laying up crazy expensive carbon fiber, putting it out on a track, and pushing it to its absolute limits. But now, imagine trying to test that exact same performance without actually building a single physical part to crash or scrap. Sounds completely impossible, right? Well, that is exactly what the top-tier designers are pulling off today. By dropping us straight onto the digital racetrack with the Italian high-performance manufacturer Dallara Automobilli, we can see exactly how this magic happens. They use these incredibly dynamic virtual environments to simulate super complex aerodynamics. So instead of spending weeks building a physical prototype just to stick it in a wind tunnel, they can test airflow, downforce, and drag entirely on a screen. I mean, we're talking about saving massive amounts of time and resources before a single piece of metal is even cut. Section 1. F1 Prototyping. The problem. Let's start by really looking at the traditional problem with high-performance auto manufacturing. Honestly, it all comes down to the staggering cost of trial and error. Think of this as the ultimate crash test analogy. On one side, you have your traditional physical prototyping. It eats up physical materials, requires huge energy inputs, and inevitably generates a massive amount of physical waste. But on the flip side, we have virtualization. Testing way wider combinations entirely digitally saves a ton of time and reduces waste to absolute zero. It's basically the difference between the massive cost of crashing real carbon fiber versus the incredible, limitless efficiency of just crashing digital pixels. Section 2. Dallara's Digital Twin Solution. So to solve this massive physical waste problem, Dallara utilizes a super technologically empowered business model innovation. They use a convergence of advanced computing, the Internet of Things, and artificial intelligence to create identical digital replicas of car engines and components. Think about that for a second. They can study the performance, tweak the fuel injection, and optimize heat distribution entirely within this digital dimension before ever manufacturing any real parts. By analyzing much wider probable combinations on these dynamic wireframes, Dallara successfully de-risks changes and modifications in incredibly complex vehicle systems. Look at it this way. If a new suspension geometry fails at 200 miles per hour, well, it fails safely in a server rack, not out on the tarmac. This allows engineers to push the boundaries of innovation way further and way faster than ever before. Section 3. What are digital twins? Now that we've seen arguably the sexiest, fastest application of this tech out on the racetrack, let's take a beat and define what this underlying technology actually is. A digital twin is a digital representation of a physical asset, featuring a real-time exchange of live data between the digital and physical components. The crucial thing to understand here is that this isn't just some simple 3D drawing or a static blueprint. No, it is a highly precise emulation fueled by continuous, real-time sensor data. The physical and digital objects are essentially talking to each other constantly. Now, while this sounds incredibly futuristic, the industrial use of this actually dates all the way back to the 1960s. NASA created and maintained an identical twin of the Apollo 11 spacecraft right here on the ground. They used telemetry data to mirror the real operating conditions in space, simulating real-time behavior to troubleshoot problems for the astronauts up in orbit. I mean, talk about the ultimate long-distance tech support, right? This life-saving historical anchor proves that from the very beginning, these dynamic models were designed to troubleshoot incredibly high-stakes physical problems from a safe distance. Remember when Apollo 13 had its critical failure? It was this exact digital twin technology, the ability to test fixes on the ground replica before sending the commands up to space, that helped bring those astronauts back home safely. Section 4. Not just a digital clone. As this technology has absolutely exploded recently, there's a massive misconception in the media that we need to decisively squash right now. You're going to hear people call basically any 3D model a digital twin. But look at the difference here. A true digital twin is a dynamic emulation with continuous live data streaming across a network. A digital clone or an avatar is just a static virtual rendering, completely lacking that live network exchange. So if your 3D model doesn't have a live data stream exchanging real-world information, stuff like temperature, stress, or vibration, it's just a digital avatar, not a true twin.
Section 5. Driving the Circular Economy.
All right, let's zoom out from Formula One for a second and see how this impacts the entire globe. Digital twins are basically the fundamental technological enablers of Industry 4.0. They are integrating our physical, digital, and even biological realms perfectly. Just imagine entire cities, power grids, or global supply chains layered with real-time digital twins monitoring and optimizing their flow.
The ultimate takeaway you should get from this is that this technology drives elite competitive performance while simultaneously saving our planet's resources. By giving us enhanced control in the physical realm through the digital world, we drastically cut down on physical defects and waste. We lower emissions, we optimize process times, we reduce system downtime, and we minimize global energy consumption. Guys, this is literally the backbone of transitioning to a truly circular economy.
By allowing for predictive, preventative, and prescriptive maintenance, industries don't just react when machines break anymore. They actually predict it digitally and fix it before it even happens. This allows manufacturers to design physical assets from the ground up to support complete disassembly, remanufacturing, and recycling. We are officially moving from an outdated take, make, dispose model to a loop of continuous, data-driven sustainability.
I want to leave you with this provocative thought as we wrap up today's explainer. If a Formula One team can test the world's most elite aerodynamics while completely eliminating physical waste, what physical prototypes could a digital twin eliminate in your industry? How can you leverage a digitally empowered circular economy to stop crushing physical materials and start innovating with data? Take a moment to really think about that. I'll catch you in the next explainer.